Okay, good morning everybody, and today I will introduce the Hubbard functionals, so DFT+U and also DFT+U+V, illustrated basic concept and applications. Okay, this is a quick outline of this presentation. So after a quick refresh of what we saw yesterday about the fundamental theory of DFT and in particular of exchange correlation functionals, I will talk about lithium-ion cathode materials. That will be the main example we will be working on today in order to understand how these Hubbard corrections work and how they achieve localization of electrons in mixed valence compound. And then I will talk about a little bit the Hubbard model and how it is interfaced, let's say, or embedded in DFT calculations with the Hubbard correction, the DFT+U corrective functionals. And then, of course, I will extend the presentation to the V, so to the interside term, in order to improve the treatment of systems that are characterized by more pronounced hybridization and covalency. And finally, I will discuss some theoretical framework of all these, which will help us to understand where these Hubbard corrections stand in the general framework that was also well illustrated yesterday by both Professor Marzari and Kronik. Okay, so let me start from discussing very briefly some fundamentals of density functional theory. We can say that the main advantages of using density functional theory instead of solving the many electron Schrödinger equation, way too complicated for us to solve, is the fact that we can rewrite everything, at least if we're interested in ground state properties, in terms of the electronic charge density, rather than using the many-body wave function. The many-body wave function on the left here is, of course, depends at least on 3n space variables, not to speak about the spin, where n is the number of electrons, while the charge density is a far simpler object to deal with because it only depends on 3 space variables, so far easier to store in a computer and much more user-friendly if you want. Of course, we need to construct a theory that allows us to do that, and that was done by Walter Kohn in the mid-60s and his co-workers by defining density functional theory. So what makes density functional theory so useful and so practical in ab initio calculation is basically the Holmberg-Kohn theorems, and in particular the possibility to write the total energy of the system as a function null of the charge density of the electrons. And in particular, we write it as the interaction of the electrons with an external potential. Here I've put simply the interaction, the Coulomb interaction, attraction to the ions of our system, plus a universal functional that, of course, is the expectation value of the kinetic energy operator and the electron-electron repulsion operator over the many-body wave function that is also functional of the density if you represent the ground state. And then, of course, the possibility to rewrite this quantity in terms of known quantities, specifically the kinetic energy of fictitious or auxiliary systems of non-interacting electrons, and an interaction density Coulomb interaction written in this way allows us to solve this problem using the Kohn-Sham scheme, basically solving a set of an Schrödinger-like single particle equation that needs to be solved self-consistently, etc. Of course, this last equality is what defines implicitly the exchange correlation functional, which is exactly the difference between these object up here in the first row minus these two other objects that we know how to construct from the the auxiliary independent electron system that we use in Conshan implementation of DFT. Now, why this is an exact rewriting of the problem? Of course, nobody knows what the exact exchange correlation function looks like, and we don't have an analytic explicit expression for this function. So that's where all the approximation goes. And that's the source, basically, of some well-known problems that we're going to deal with today. Okay, so in order to discuss now some notable problems coming from the approximation that we make on the exchange correlation term, as I said before, we'll focus on studying the cathode materials for rechargeable lithium-ion batteries. This is a cartoon showing how a lithium-ion battery is composed and how it works. And I will focus specifically on the materials that was also mentioned, the class of material that was also mentioned by Professor Mazzari yesterday morning, basically the phosphate of transition metal and lithium that is a class of system we worked on mostly recently. This is a class of so-called intercalation cathode materials because lithium is able to go in and out without major structural changes in the hosting crystal. But that's actually not very important. What we want to focus on is the way the battery works, and specifically on the quantitative energetics of its working. So what we can say, broadly speaking, is that lithium is attracted to the cathode during the discharge of the battery. That's when we use it, basically. Lithium travels through the electrolyte as an ion, as positive ion. The electron is forced to travel along the external circuit. That's when we use its power. And lithium is attracted to the cathode from the anode just because we say its chemical potential is lower than it is in the anode. And the source of this lower chemical potential is actually the fact that the transition metal that's in the cathode gets reduced. Basically, the electron that used to be with the lithium in the anode can fall into a deeper energy well in the cathode because it gets attached to the transition metal. It can reduce the transition metal. So the fundamental ingredient in the cathode material is a transition metal capable to undergo a shift in its valence state, in this case between 3+ and 2+ states, and that's what powers basically the battery. So if we want to basically run calculations that are quantitatively predictive for this class of materials, we need to be able to capture this chemistry, basically the redox chemistry of the transition metal that enter the composition of the cathode materials. Now let's study this using a simple cartoon where we only have transition metals represented by these bigger balls whose color indicates that the valence states. Basically, lighter blue is for 3+ states and darker blue is for 2+, while lithium is represented by the small dots. Okay, so we start from a situation like this where we have the fully charged battery and the fully dilithiated cathode material with all light blues and no lithium in the structure. We end up when the battery is fully discharged with all the lithium in the cathode and all the transition metals basically in the 2+ states. Okay, so these little balls actually represent lithium plus nominally. So there are several questions. The main two we want to answer is basically what is the energetics of this problem, of this process, and what happens in between during the charge or the discharge of the battery in terms of basically in terms of materials that are involved in the construction of the cathode. Now, a useful hint of what happens comes from experiments, actually, that says that in between these two states, the fully charged and fully discharged, this is the charged cathode, this is discharged cathode, the batteries, at least when the transition metal is iron, which is the one that's commercially available nowadays in lithium-ion batteries, the battery features a nice plateau of the voltage. So basically the voltage doesn't basically change in between these two states, except of course for small region around here and around here, which we'll neglect today. And that's not a trivial statement to do from the point of view of the cathode, because it means that basically no new phase forms at intermediate concentration of lithium. So basically what we have in between these two stages is basically this phase, a little bit of this phase, and a little bit of this phase that don't mix with each other. So lithium, while arriving to the cathode, basically let the lithium-rich phase grow at the expense of the other lithium-poor phase, the lithiated phase, that shrinks correspondingly. And this is what we have, except for a thin interface region, which we will neglect today in the thermodynamic limit. So if we want to represent this intermediate situation with the same cartoon, we have something like this. So we have to find something like this. And if our simulation is good, we should find that these basically this is the most favorable intermediate situation. Okay, so let's speak about average voltages and formation energy of intermediate phase. The average voltages depends on the total energy difference between these the lithiated states and the fully lithiated one, while the formation energy compares the energy of anything that we can imagine at intermediate lithium concentration compared to the corresponding linear combination of the energy of the other two phases, the lithiated one and the fully lithiated one. So this formation energy should be positive for anything we can imagine in between, because we need to obtain that the no intermediate phase forms, okay? While we need an accurate energetics for this phase and for this phase if we want to capture the average voltage of the battery. So anything that can form either ordered arrangements of lithium or disordered one should have higher energy than the linear combination of the other two. Now let's verify whether this is the case that we obtain or not. In this slide, I will focus on the olivine cathode material based on cobalt, because it's a nice simple example that we want to start from. And I will look into the total occupation of these states of the transition metal that are computed like the trace of the occupation matrix, where the occupation matrix, that's also the one that we use in the +U functional, is obtained from a projection of Kohn-Sham states, this psi k of K and V, where K is the K point and V is the band index and sigma is the spin, onto atomic states. So basically these are the atomic D states of cobalt, okay? So we want to compare what we have in terms of these numbers for the fully lithiated one, where cobalt is 2+, and fully dilithiated one, where cobalt is 3+, with anything that we have in between. So for us to obtain the correct energetics, in between we need to obtain that the electron sticks with the transition metal. So for any intermediate lithium concentration, we need to have basically what is called a mixed valence state with a collection of 2+ and 3+ cobalt, with a collection of cobalt ion in 2+ and 3+. So for example, if we have a half of the lithium, the maximum lithium possible that the structure can take, we should have half of the cobalt in the 2+ states and the other half in the 3+ states. Now, is this the case if we use any of the standard approximate functional? Well, ideally, we want to have, again, this number to reproduce for this one here for the 2+ states, and this number here for the 3+ states. This is not the case with standard DFT approximation for the exchange correlation function, and as you see, we basically get something in between. So it's as if all cobalts are actually in a sort of 2.5+ states, which is not what we want, which is represented here by an ordered phase of lithium, but a spread out electrons. So you see an intermediate color of all the transition metals in between these two extremes. And that also reverberates negatively on the energetics. So we get negative formation energy for this intermediate phase, which is predicted to be stable compared to the linear combination of the other two, and an underestimation of the voltage, which is not pleasant to deal with. So how do we want to change this? How we want to fix this situation? Basically, we know that is due to the fact that most of the approximation on the exchange correlation function are based on the homogeneous electron gas, so which of course favors metallic ground state and over delocalization of electrons, etc. So we want to use a model Hamiltonian, the Hubbard Hamiltonian, that is actually much more well suited to capture also electronic correlation when the interaction between electrons becomes stronger. Okay, so this is the simplest version of the Hubbard Hamiltonian, where T is the OP amplitude, basically the bandwidth or the dispersion of bands, which we have in every tie binding approximation, and U represent the repulsion between electrons when they are on the same side. So these two simple ingredients are in the Hamiltonian, and this model is already capable of capturing the localization of electrons. So here we have one orbital per side and one electron per side. That means half filling. Okay. In a band structure language, which is the one that we naturally use in approximate DFT, that would imply a metallic ground state, okay, because we half fill a band, and that's no way to escape having the half filled band of in this case 3D states. But of course, this is not a metal, and at least if U becomes bigger. So if the kinetic energy, or if you want the single particle energy, prevails on the Coulomb repulsion between electrons, then yes, we can say that the electronic system is delocalized. Okay, so the kinetic energy is the main character of this system. However, if U grows bigger, we should obtain, and this model is able to capture this transition, an insulated ground state, okay? Just because the electrons don't have enough energy to jump on the next side of the lattice and to compensate for the repulsion that they feel when they approach these other sides. Now, the idea is to use this simple model embedded in DFT and use it to describe the physics, basically, of at least of the localized state, these states that we have in our material. So this is the basic idea DFT+U is based on, and how do we embed this Hubbard model into the DFT? Basically, we take the usual DFT function, a function of the charge density. We construct the occupations of the D states or F states or whatever manifold of localized states we have in our system. And we add an Hubbard, so-called Hubbard, representation of the Hubbard energy based on as a function of these occupation numbers. And we take off some some terms that supposedly captures basically what how much of that correlation or is already contained in the approximate exchange correlation function, so to avoid so-called double counting problems. Now, as was mentioned yesterday by Professor Mazzari, DFT+U was introduced in the early 90s by Anisimov and co-worker, and these are two of the early papers on this method. Through the years, there has been a lot of development, of course, and a nice formulation was given in 95 by Liechtenstein and his co-workers, who came up with a so-called rotational invariant expression based on screened artery fork, basically, where you have basically that the effective interactions changes accordingly to the rotation of these states on the same site, so to compensate the rotation of the operatorial part. These are not operator, of course, in DFT. These are expectation values, but that's not very important. And the double counting term is computed in the limit of full occupation of these electronic states. Now, we will focus on a simpler expression that was also introduced yesterday by Professor Mazzari, which is due to Dudarev and goes back to 98, which is given in this formula here, where we have the U, this is still the Hubbard U, representing the interaction between electrons on the same site, on the same Hubbard site, times the trace of Ni 1 minus Ni. So Ni is the occupational matrix of the ion, of the cobalt, let's say, ion that we're considering. So we multiply Ni times 1 minus Ni, and so you see what you get basically is a constraint that pushes the system towards having Ni basically equal to Ni squared. So a so-called idempotent occupation matrix. So how it works, again, this is the definition of the occupation matrix as a projection onto atomic states, of which you get a representation down here. And in order to understand how it works, how it basically you have to keep in mind that it only acts on localized states. And if we look at the potential, we can do that using basically the diagonal representation, because we still have a rotational invariant formulation for this corrective functional. Okay, so in this framework where we have diagonalized this occupation matrix, we have lambda I 1 minus lambda I, where these lambdas are the eigenvalues of the occupation. So if we construct the way the potential acts on this piece of the potential, the Hubbard piece of the potential acts on the constant state, which we can compute this way as a functional derivative of the EU with respect to the psi star, you get something like this, basically. So it's a simple derivative of this with respect to lambda, and then the derivative of lambda with respect to psi star, you get something like this. And you see immediately that if lambda exceeds half occupation, so if the state is more than half occupied, the potential is attractive and favors further occupation of that state. The opposite happens basically if lambda is smaller than 1/2 to start with, so that the potential becomes repulsive and pushes the electron away in order to favor the states to become empty. So a gap basically opens in the spectrum, of the quantum spectrum of the system between fully occupied and fully unoccupied states, which is due to the action of this Hubbard correction. Does it work? Let's see. Let's see for the example that we were studying before. So we know already this result. We know we don't like these average numbers here. Let's see if with this Hubbard correction we can fix this situation. Turns out that yes, we can do that. So instead we will have a collection of 2+ and 3+ cobalt that have occupation numbers almost perfectly in line with the 2+ and 3+ occupation number that we can detect in the fully lithiated compounds and fully dilithiated ones, respectively. Does the energetic improve in this case? So in the cartoon language, of course, we have an ordered phase of 2+ and 3+, and we should have a positive formation energy for these states compared to the linear combination of the energy of the two. And that's exactly what we get. Most notably, we get a much better approximation for the average voltage of these systems that amounts to 4.82 compared to 4.8 from the experiment. So it does work in a very good way. And that's not the only case. So in literature, you can find many other instances where DFT+U basically is effective in favoring localization of electrons. Here is another example dealing with the localization of electrons left behind from oxygen vacancy in strontium titanate. You see that with DFT, you get a delocalized, basically charge density of electrons, while you get a nice localization with DFT+U and also with the +V, which we'll talk about later. And the same thing actually happens in Syria, where you have the oxygen vacancy leaving behind 2 electrons that are delocalized as usual in DFT, but far more localized with the Hubbard correction. Another class of paradigmatic example where this material has been usefully adopted is transition metal monoxides. You will practice on them this afternoon in the practical section, hands-on session. So these transition metal monoxide typically have a rock salt structure where, however, they have an antiferromagnetic ground state of the kind illustrated in this figure on the left here, and the 3 vectors illustrated here are the magnetic unit cell of these materials, and they are typically difficult to get. They're all insulators, but DFT typically predict either metals or insulators with a smaller band gap. So for cobalt, using the DFT+U, you can switch from a metallic ground state to a nice insulator one. For iron oxide, it even actually you will practice on the cobalt oxide in the hands-on section. For iron oxide, the situation is a little more complicated. I will put the reference in a second, because in order to capture the lowest energy ground state, you need to break the symmetry. That's something that we will talk about in the last part of this presentation. And you need to get basically an orbitally ordered state that is also helpful in capturing some the rhombohedral distortion this material undergoes under pressure. This is you will see also iron oxide this afternoon, but not in the orbitally ordered phase, because it has a fairly bigger unit cell, and that makes a calculation too expensive for us to run in the hands-on section. You will also hear later on about the effect of the Hubbard correction on lattice vibration from Andrea Floris. Probably we'll talk about and we'll illustrate these cases, manganese oxide and nickel oxide, in a little more detail than I can do here. And also you will hear an invited lecture by Renata Venskovic later on, probably talking about how this better localization of electrons on the D states of iron that you can achieve with DFT+U is very important to capture the thermomechanical properties of minerals in the Earth interior, where the concentration of iron grows with depth from the Earth's surface, and is fundamental to capture basically the structural and spin transition these materials undergo under the pressure and temperature conditions they are subjected to in our planets in the interior. Okay, so I won't talk in details about this because you will see dedicated presentation later on today. And of course, you can find many other examples in literature of success stories of the use of DFT+U. Here's a quick example illustrating how the improvement that you can get, for example, in deposition of Raman active peaks in the lattice vibration of lithium cobalt oxide and this mixed transition metal oxide. Those are also cathode materials for lithium-ion batteries. So you see the nice agreement between GGA+U calculation and experiments in both cases compared to a poorer agreement that you can get with standard approximation of exchange correlation function. Let me go on now in discussing the localization of electrons in cases where you get significant hybridization. So this will take us to a material. This can be done basically discussing a material, still a lithium-ion battery cathode materials that's in the same family as the cobalt one we have discussed so far, but that's based on manganese. Okay, so we want to do basically the same as we were doing before, checking whether in this case we also get a nice mixed valence ground state for when the material basically only contains half of the lithium it can take. If you do, of course, calculations with DFT, you don't expect much because we have learned this lesson before with the cobalt material. However, if you try with the standard +U correction, you still don't get very good results. And if you check the energetics, you see that although you have positive formation energy, the voltage is yes improved with respect to the plain DFT, but not too accurate compared to the experimental plateau. Okay, so what's going on? Basically, it turns out that manganese compared to cobalt features more hybridization, a more pronounced hybridization with the surrounding oxygens. So localization is not an atomic affair anymore as it was before, and you need to capture these more pronounced hybridization with oxygen. So instead of using the simple Hubbard model I was discussing before, we use an extended version that also includes the interaction between electrons not only on the same atomic side, but also between neighbor sites. You can have nearest neighbor interaction, second nearest neighbor interaction. You will also see this afternoon when we do the hands-on section. And if we do the same algebra as before to get a corrective functional for our DFT calculation, you end up with this formulation of the Hubbard correction for your density functional theory function, okay? Where you need also an extended formulation for the occupation number that now allow you to take atomic states from neighbor atoms, okay? So you have two terms now, the usual one that tries to localize electrons on the same Hubbard side, and the one circled in blue, the new one that instead describes interaction between neighbor sites and tries to favor localization on hybridized states, basically on bonds, if you want. So there's competition in between them, and the ground state that you end up finding at the end of the calculation critically depends on the relative value of U and V that you need to be able to compute now more critically than before, because you had one parameter, now you have two in your calculation, and what you get now depends critically on the balance between these two numbers. So you have a nice tool now that basically allows you to capture electron localization in presence of hybridization, but you need to be able to compute, and you will see how to compute this in the next talk about Yuri Timrov. Does it work? Well, pleasantly, the answer is yes. And we see that at intermediate lithium concentration, we again achieved a mixed valence ground state with 2+ having the same occupation number basically of the 2+ in fully lithiated material, and the same thing for the 3+. And the voltage also improves. You see here a much closer representation of the experimental value that you can get also within this approach. What about the iron material? Well, the iron material that works already well with the +U equally well works with the +V, and that also refines quantitatively the prediction on the voltage. So it's a nice extension in the sense that never worsen the prediction of the +U, only approximation, and occasionally does better. This is a more difficult case we studied more recently in this paper that just came out, and shows, as Nicola also was mentioning yesterday, this digital shift in the valence states of iron and manganese. Here the difficulty is not only that the transition metal has to switch state between 2+ and 3+ in a digital manner as a function of lithium concentration, but also you need to get manganese to switch it before iron, because it has a higher potential. And that's what nicely we get with these +U+V approximations. Also HSC is able to do that, but less precisely, as you can see from this plot. And correspondingly, we get a very good approximation of the experimental voltage for all these intermediate composition, which is quite pleasant to get. Now, let me discuss bound semiconductors. This might seem an unusual thing to do. Actually, there were some questions yesterday I saw on Slack about this. Why should one want to use Hubbard correction on silicon and gallium arsenide, which are not most notably correlated materials or strongly localized material? It's because precisely for what also Nicola was saying yesterday, Nicola Marzari, this +U correction does, in a sense, the same job as hybrid functionals, or basically aiming at the correction of the spurious self-interaction. We still have an approximate exchange correlation function. So if we want to check that this works this way, we better have some calculation done on these materials that typically are improved by hybrid function, but using hybrid functional and or SiC kind of approaches. Now, of course, these are not systems where you get localization of electrons on single atoms. Rather, you have sp3 kind of bonds between atoms, so you better use the +V approximation. And in fact, you see here in this band structure, compare what you get in the plane DFT, which is the dashed lines, with DFT+U+V results, and you see a nice improvement of the width of the band gap, and also the +V is able to refine the prediction of other properties like the equilibrium lattice parameter, the bulk modulus, etc. So you see here the experimental value for all this quantity, and how close or how distant the GGA prediction is. And the +U, of course, only can improve some of that, but fails in improving the band gap, just because favoring basically integer occupation on each site suppresses the hybridization between sites, which is so important for this material, and basically have the band gap on whose band gaps is basically between bonding and anti-bonding states. Okay, so if you suppress hybridization, you suppress this band gap, and you go the opposite way you should. While +V restores this localization pattern, and predict much better band gaps, bulk moduli, and also does well in predicting equilibrium lattice parameter. People have refined these over the years, have refined this calculation and show that the plus V function is also able to refine the prediction on the phonon dispersion and phonon lifetime and thermal conductivity of these materials. And you can find the application, nice discussion of the application of plus V for zirconium silicon selenide and also 2D materials like graphene in comparison with hybrid functional and actually GW. In this other paper, they were studying instead the structural distortion of perovskite and studying in particular the electron phonon matrix element and showing that the plus V, the use of plus V was required actually to get results in consistency with those of the hybrid functional. Now, if I'm allowed to speak 5 more minutes, I will go briefly through the theoretical part, which will help us to frame all this into what was discussed yesterday morning. So I will only take a few minutes here. So let's review now what the delocalization error is actually in this calculation. So suppose that you are trying to dissociate the H2 plus molecule, which is represented by these cartoons again. Now, what you get in the exact world, let's say in the real world, is that at a certain point, the electron localizes either on one atom or the other one, okay? And if you call ρ1 and ρ2 the two densities, you have those two solutions have equal probability, of course, because of the symmetry of the system. If you do with an approximate exchange correlation function using DFT, you end up with something like this, half spin on each site independently of the distance. And this is not actually wrong from the point of view of DFT because it conveys the idea that these two solutions, okay, have equal probability. So if you overlap the two density, you actually end up with something like this, okay? The problem is that the energy is not right. So in here, of course, you have to have that the energy is a linear combination of the two or equal to the energy of isolated ions, and you don't get anything like that in here. And that was nicely discussed in the paper that also Professor Mazzari was referring to yesterday, where you see that the R3 Fock is exact for the correlation error for one electron system, basically, and DFT functional of various kind instead fail in this prediction. Another error that's typically discussed in literature is called the so-called strong correlation error, and can be exemplified by referring to the splitting of H2 molecule. Now, not anymore the H2 plus, but H2 with 2 electrons. Again, if you do in the real world, you end up with 2 solutions with the ground state basically will be 1 electron localized on each state, and so you get many solutions. And just to represent it here, all degenerate to each other because the 2 ions will be far apart from one another. And again, because of the asymmetry of the system with the approximate DFT, you always get a alpha spin on each ion at the end, independently of the distance. And again, the charge density is not bad in the sense that it conveys the idea that it's a linear combination of these other two with equal probability. But unfortunately, again, the energy is not what you expect to be, and shows some curvature again that shouldn't be there. Okay, so you should be getting a linear combination of the two extrema, while you get some curve that basically is telling you that the energy is not predicted well. Well, this problem was recognized early on in in the early 80s, when people started to develop functionals more actively, and was studied in particular by John Perdue and his co-workers, who said that if you have a system in contact with a reservoir with which it can exchange electrons, then the energy should have a piecewise linear behavior, and this is very important because also the chemical potential shift. The chemical potential should be discontinuous in correspondence of integer occupation. The chemical potential is basically the slope of these segments, and the difference in the slope at 0 at integer occupation has an important physical meaning, that is the fundamental gap of the system, basically the difference between ionization potential and electron affinity, which you miss if instead you have an analytic behavior of the energy with respect to the number of electrons, as you have in the standard approximation of DFT. And that's the reason basically why we get always an underestimation of the band gap. You will hear more about this also in the Koopman days tomorrow, where all these problems are again revisited. Now, one may think, okay, since in the last 40 years there's been much development in the functionals, but still even the scan functional has the same type of problems, because it's an inherent problem of basically quantum DFT. This curvature problem and excessive curvature of the energy that needs to be taken away somehow, and that's also a problem that afflicts calculation on solids, a periodic system where you might have localized states, and you can think of them as immersed in a bath represented by the rest of the crystal or of the molecule, if you prefer, with which they can exchange electrons. So in a sense, it's the same thing here that's missing. And that's why when we have transition metals or rare earth metals with localized states, we typically get into trouble if we use a standard approximation, because the energetics of electron exchange with the rest of the crystal is not captured very well by standard approximations. And that can lead to significant error, like I showed before, also for the magnetic properties. For example, underestimation of magnetic moments, localized magnetic moments, or overestimation of magnetic interaction between sites are the typical consequence of this over-delocalization of D or F electrons over the unit cell. Now, in a way, this is not dissimilar to what chemistry we have in chemistry in the representation of the benzene molecules, right? When you have when you understand the benzene ground state as a resonance between these two, well, there could be more Kekule structures, okay? In a sense, if some states are degenerate by symmetry, they may result fractionally occupied, and that's typically associated with metallic delocalization. The problem is that when you get some metallic density, the approximate functional is not able to recognize that it results from the resonance, let's say, of insulated ground state. So the problem is here in the fact that it doesn't recognize it as a superposition of lower symmetry solutions. So typically, in order to get better localization of electrons, you need to break some symmetry broken, and to allow for that localization in this sense. In any case, what the DFT+U in its simplest version does is exactly this. It tries to restore the piecewise linearity of the energy, just starting from the approximate analytic behavior or sort of analytic behavior of the approximate energy functional by adding this term here that is exactly represented by the blue curve on the bottom here. So that the blue curve, which simplify what this term does, is exactly what you need to recover the piecewise linearity from the black curve. So provided that the U is measured correctly, as you will see in the next talk. This is the main idea. So just to conclude, let me go back to iron oxide, which is a nice example of what I was saying about symmetry breaking and localization. So you get a metallic ground state as usual from approximate DFT, and the reason is that the last electron, downspin electron, is sitting on a doublet of EG states. And you can do two things here to localize it. Do the simple way, which you will see this afternoon in the hands-on, and try to localize the electrons. Try to suggest the code to localize this electron on this A1G state, which will be taken down in energy, so that a gap can open between this one and the EG states that he was sitting on before. Or you can break the symmetry in another way and have this symmetric state as a resonance, basically between these two states where you have broken this EG degeneracy. And this requires a much larger supercell, well, much larger. It's a threefold supercell, you see, and that also implies orbital ordering of the iron D states, but gets lower energy. So in this case, you get lower energy by orbitally ordering, and that's a nice simplification of what I was mentioning before with the benzene molecules. Okay, so I will leave the summary with you because I ran out of time, and so I will thank you for all the attention, and I will be happy to take questions if time allows. Thank you.
Thanks a lot, Matteo, for the very nice talk and broad overview on DFT+U. So I think, yeah, we had a lot of questions on the Slack. Many of those have been already addressed by the people, but there are a few that are still there, and maybe I can read some for you. So there's a question by Tran Wang. He was asking, we compute the matrix element of the Coulomb operator between two electron state using Slater integrals. Is the reason we put it as U parameter from the screening effect? So I guess the
reason for what? I didn't understand the last part.
Is the reason we put it as U parameter, so this Coulomb integral, we use it as U parameter from the screening effect. Maybe the question is related to, how to include screening in this electron.
So that's true formally, in the sense that, especially in the early implementation of DFT+U, it was proposed, or if you wanted Liechtenstein that I showed before. Let me fish it out. So in this implementation here, we have exactly this, that formally we have this effective interaction being expressed as a Coulomb interaction between local Coulomb interaction integrals, double integrals between atomic states, atomic D states. Now we need them to be screened. Okay, we need the effective interactions. So what typically people do is to extract somehow their average U and J or V or whatever from some DFT calculations, and then use a relation between these objects here and their atomic average, okay, in order to extract back these properties. Now, in the simplest approximation that we focused on, we don't have those effective interaction in the Hartree-Fock expression anymore. However, I seem to remember the ACBN0 way of calculating U and V is still based on computing the Coulomb integrals over atomic states, and then screening them with the occupation, somehow working with the occupations. Okay, so that's still important. I don't know if I answered the questions.
Thank you, Matteo. And there is also another question that, I mean, a very long one. Yuri went through it very carefully, but there is still something that probably is important to ask you. So the question is the piecewise linearity and derivative discontinuities the unique origin or reason behind the band gap issue in density functional theory?
Yes and no, in the sense that when you have an approximate functional that misses, so the band gap, as was said yesterday, I believe by your chronic, the fundamental band gap is the sum of two pieces. So it's the Kohn-Sham band gap plus the potential discontinuity. The potential discontinuity is typically missed by approximate functionals. When you have when you work with an approximate functional, so you miss that part, but you also misrepresent the first part. The Kohn-Sham gap is not what you would get with the exact functional. Now, the exact functional would have in his Kohn-Sham spectrum only the Kohn-Sham part of the band gap. So that would still not be the fundamental band gap. But from total energy calculation with a different number of electrons, you could recover the discontinuity of the potential and add to the Kohn-Sham gap and get the exact fundamental band gap. So what the +U does is something in between, actually, because it tries to reinsert this the effect of this potential discontinuity. In a sense, this is its way to reintroduce some discontinuity in the potential into the Kohn-Sham gap, into the Kohn-Sham band spectrum. Okay, so it tries to open the gap due to this potential discontinuity into the Kohn-Sham spectrum. Okay, and in doing that, we see improvement also of other properties. That's more or less what's going on here.